Hey everybody, we're going to learn a little bit more about memorization in machine learning today, particularly focused on how training and evaluation happens. So, what if I asked you this image on the screen? What if I asked you, is this a good representation of a swing? What would you say? Is this what you think of when you think of a swing? Is this good for a machine learning model to think of a swing? Or machine learning models don't think, but to process an image like this and return a swing. My second question for you is, if I told you that the training data set has the image on the left and the test data set has the image on the right, do you think that you would describe the test image as unseen or as data that is supremely separate and different than the training data? I think we can both see that the images are quite similar, that they're taken on the same day, likely by the same photographer, in the same room with the same person. So when we think about how we evaluate, how we both train and evaluate machine learning models, they both have a strong impact on the types of machine learning models that we build, on how good the machine learning models are that we build. And that's what this article this week is about. I'm going to take you through how an actual training round of a machine learning, a deep learning model works to kind of give you an idea of what happens. First, we have all of our data. This is the data, again, that has that long tail distribution that we talked about a few videos ago. So we know in the head there's a lot of duplication. There's also the popular content, so to speak, we can think of in the head. And then in the tail, we have this really, really long tail in comparison to the examples in the head. And this long, long tail is kind of like everything else in the world. And one question that I have for us is, can we actually really learn to represent the whole world in a machine learning model? Maybe this is a question that we have to philosophically debate when we think about how this happens, how memorization happens, and why it is that what I'm going to talk about today is maybe not perhaps a very good representation of learning and intelligence. So when we have a deep learning model, we have that whole data. We kind of split off a bit from that same data. We say this is the unseen testing data. So that's maybe the first question that we have. Is it useful to have the test data from the same distribution as the training data? It's easy for us to do because we already have the data. Whether it truly tests what we're trying to test when we evaluate performance is another question. Then we take the training data, and within that training data, as I'm showing here on the screen, we develop batches. And these batches, we're going to eventually show the model or process essentially through the model and get a prediction. Now, with our training data, we also have the true labels or the outcome that we expect. In a language model, that would be the next token. We know the next token that was in the original text. And with the computer vision model, it's likely the labels. So, for example, in the images that you just saw, it's swing. And we're going to take these batches, we're going to divide them up pseudo-randomly from the training data, and then we're going to essentially process it through the model and ask for a prediction. In the beginning, the predictions will be full of a bunch of errors. It won't be very good at all. And then as we train, the goal is to improve the predictions so that they're better. Well, how does that happen? We process the data through, and here let's say that we're doing computer vision, and let's say that the training input is this photo of, it's just an image as you can see, but we can imagine a photo of a succulent or a cactus. And let's say the model returns a probability, the highest probability being that it's a turtle. Okay, well, what does this mean? How do we calculate the error? Essentially, we build loss functions, is what we call them, that tries to then attribute, or that essentially does attribute the error in the outcome to errors or updates that we want to make in each of the little nodes in a deep learning model. So in a deep learning model, we have an architecture that we've chosen, which usually has many different layers of different sorts. And within those layers, there's, we used to call them neurons, but you can think of them as little nodes. And in these nodes, there's variables. And there can also be variables in numerous equations in between layers. But to not overcomplicate it, we essentially want to take those variables, and if that particular node, so here, for example, this one with the very thick red outline that I've had, maybe that node contributed very strongly to the outcome that was an erroneous prediction. Well, then we'd want to greatly update that node until it gives a better outcome of the prediction. So we will maybe drastically change the variables in that node, or we might just change a little bit at a time and slowly try to move closer to having accurate predictions. And this is something that is then done with each batch until we've gone through all the training data. That's called an epoch. And then we do it again through all of the training data again, and then we do it again and again and again. And in today's largest models, the training data is potentially used hundreds of thousands of times before the training is stopped. Between showing all of the training data and sometimes a little bit interspersed in an epoch, we also validate on the test data. We show the test data and then we get an error on the test data. Now, again, this test data is supposed to be totally unseen. And yet we see the example of the swing. There's numerous other examples, and I'll post a link for some examples you can look at. But supposedly this is unseen, and yet a lot of teams will decide, or if you automate it, your automation will decide when the test error reaches this low, then stop training. We can see that perhaps there is an over-optimization on the way we evaluate and also the way that we train, where it might be useful mathematically to memorize some of the data, particularly if indeed the data will be in the test data set, and particularly if the team is evaluating the model based on test data performance. I'll then just briefly touch on benchmarks and leaderboard culture. So this idea of getting the best accuracy on something, this idea that if you beat a benchmark, you might have heard about models that beat the bar exam or models that are as smart as a sixth grader in math. A lot of these claims come from so-called benchmarks. I think the original intention behind benchmarks was to truly create interesting unseen data, but there is an intense pressure to publish machine learning research. And if you've ever done a PhD in machine learning, you know that publishing is kind of a life or death for a lot of machine learning groups and also you as an individual student. And usually benchmarks mean you can publish an article that gets widely received. So publishing new benchmarks and even benchmarks that start to be like, what are we actually testing, is incentivized by academia culture and publishing culture. And then beating those benchmarks is a new paper. And also beating those benchmarks, even if you're not a machine learning researcher, but you're just a hobbyist or you're a practitioner, becomes also another proud thing you can put on your LinkedIn profile or somewhere, because the idea of beating a leaderboard, which may be an amalgamation of benchmarks or one particular benchmark, but showing up on a leaderboard, you can say that, oh yeah, I'm the number one model on this. I trained the number one model on this. You can imagine that this incentivizes people to find ways to make the model perform even better and even better, even if that means, and there has been numerous cases of actually finding the test data and training directly on the test data. Now, obviously, this isn't the point of test data. Test data should be unseen if we want to use it for validation. And yet, This has happened more than once, many times. I assume if we were to actually look into every single leaderboard example, and this creates an incentivization problem. And I would argue also a cultural problem around how we truly evaluate. Are we using machine learning to solve the problems that we want? Are we evaluating machine learning in a reasonable way? And if not, how do we create reasonable ways to evaluate that perhaps disincentivize some of the problems we see today and also some of the unintended problems, one of which is memorization in deep learning systems? So I leave you with that. And I'm excited to dive further into memorization next week. If you have feedback, questions, comments, please leave them below.